Hey Chemsters, this is Mrs. Vandalay bringing you Chemster video for Chapter 5, Section 3, Part 2. And I left off with the atomic radii, and I just want to review real quick before we go to the next page. The atomic radii, again, as you go across the period, goes down. Why? Because the attraction increases. The attraction between what? The outermost electrons and the protons in the nucleus. And what happens when you go down a period? Look what's happening. Those circles are getting bigger. Those numbers are getting bigger. The atomic radii gets bigger. Why? Because you have more shells, and those outermost electrons are further away from the nucleus than the shell before that. So go to the next page. This is where we left off in our notes. We just finished this discussion. So turn to the next page, and let's see what we did there. So this few questions, 5 questions, is asking you to interpret the graph. And after grading 2/3 of your graphs from Wednesday, that some of you really need to pay closer attention to interpretations. I had a lot of folks that graphed atomic radius and said, oh, it goes down. Well, it goes down in sections, but then it goes back up again. So you really need to be more careful in your description. I didn't really take off unless it was just it fluctuated, which really doesn't tell me much of a trend. But let's analyze this graph a little more carefully. Notice how they divided this up. The yellows here are going down a group. The blues are going down the group. These are your alkali metals. These are your group 1s. These are your noble gases, group 18. Okay, so you can kind of see what's going on with going down a group. But what else do they tell you? Within a period, I'm sorry, I said that wrong. It's going up as you go down a group. But what's happening as you go across the period? So here's one period, here's another period with a few little blips, and here is another period. So go ahead and pause this, answer these 5 questions, and then come back and see how you did. All right, welcome back. Hopefully you answered those questions. And so what element is atomic radii closest to 200 picometers? So I'm doing this, Well, sodium does. Potassium, no, potassium's up here, the element after potassium, and I really don't see any other choices. So I think it's this red dot right here. Well, what is the element after potassium? Do you have a periodic table that you can look at? You have so many of them, you shouldn't be missing any periodic tables. I said it was, calcium. Okay, that's the element after potassium, I hope. And then as you go across the period, so look at this section right here. What's happening? Going down, going down, like my sound effects, going down. So I think your answer here is it goes down. Then as you go down a group, what happens to the atomic radii? Well, what's this trend here? It's getting bigger, isn't it? It goes up. So what would be barium? Where's barium? I don't know. Barium's not on my chart. Well, cesium is. Cesium is atomic number 55. So where do you think barium is going to be? Right next to it. So what did you say there? It's going to be smaller because you're going across the period. And then what about francium? Where's francium? It's not on the graph. How am I supposed to know? Well, where is francium on the periodic table? Isn't it under cesium? So where do you think the next yellow dot's going to be? Greater than or smaller than the yellow dot of cesium? I sure hope you said, well, I wrote larger instead of greater. Sorry. I think you get the right idea, though. Okay, so does this help you interpret all your graphs that you drew? Okay, I hope so. Okay, so let's go on to the next question. So let's put this whole thing together, okay? So as I go across the period, all right, as I'm going this direction, what's happening? The attraction is going up. Why? More protons. So as attraction goes up, what happens to the size? It gets smaller. So as I go over to this side, what happens to the atomic radii? It gets bigger. So what about as I go down? Well, what happens down here? I get more shells. So these are your biggest. What about as you are at the top? They're your smallest. So in general, what element do you think is your smallest element overall? If you look, Here, it's smaller over here, and on top it is helium. And by golly, you're right, it is helium. So which do you think is my biggest element of all? By golly, it is francium. So hey folks, when element 119 comes, that's 8s1. What do you think the new biggest element's going to be? Whatever that is. I think they should call it like van der Waalium, but whatever. Okay, so go ahead and answer these 3 questions. Go ahead and pause this and answer it and see how you do. Make sure you get the right explanations, okay? So pause this and come back when you're done. Okay, welcome back. Well, first of all, what's the relationship between lithium and boron? Here's lithium and here's boron. So they are in the what? Same period. Okay, so I'll just put it over here. So which one is going to be bigger if it's in the same period? Okay, is it the one to the right or the one to the left? Well, hopefully you'll say the one to the left. Okay, why? Well, boron has more protons, more attraction, is closer together. So it's not boron, is it? All right, so if you want to word it a little bit differently, lithium has fewer protons, less attraction, and then further apart. Just like those people you don't know walking down the hall. They're like, I'm not too attracted to them. I'm going to give them a little bit of space here. All right, so you can word that any way you want as long as the logic is correct, okay? So what about the relationship between magnesium and barium? Well, here's magnesium and here's barium over here. What's their relationship? They're in the same group, aren't they? So which one's going to be bigger, the magnesium or the barium? Hopefully you got barium. Why? Make sure you get this, all right? Barium has more shells, therefore it is, the electrons is further apart than from the nucleus, okay? Now, what about phosphorus and strontium? All right, so let's find strontium and phosphorus. So here's phosphorus right here. And here is, strontium is right here. So we're going in kind of like this diagonal direction, okay? So are they in the same group? No. Are they in the same period? No, they're neither. So then what? All right? How do you decide? Okay. Well, remember what I said earlier. If the diagonal is going in that direction and a positive slope, it's a no-brainer. Okay, it's when it goes the other direction, like, I'm not really sure. I can make an argument one or the other way. But this way, it should be pretty obvious, okay? I'm hoping you said strontium's bigger. Why? Well, this is what I wrote. Strontium has more shells than magnesium. Why did you pick magnesium? Magnesium's not there. Oh, but magnesium's in the same period as phosphorus, isn't it? So strontium has more shells than magnesium, so strontium is bigger than magnesium. And phosphorus has more protons than magnesium, so therefore more attraction, they're close together, therefore magnesium is greater than phosphorus. So if strontium is bigger than magnesium and magnesium is bigger than phosphorus, therefore strontium is greater than phosphorus. Now, do you really need to explain that detail? It'd be nice, all right, to introduce that magnesium, which has that commonality of the same group and same period as the other two you're looking at. But in general, it has more shells and fewer protons, relatively speaking. There's an actual term for it. It's called effective nuclear charge. Strontium will definitely be the largest. But I'd kind of go in that direction, okay? So what I'd like you to do now is finish this off this section and do the rest of this page. So pause this, do this page, and come back, okay? All right, so what's going on with lithium and potassium? I hope, again, you have a periodic table in front of you. So what's the relationship between lithium and potassium? They're in the same group, okay, the same family. So which one is going to be bigger? Hopefully you picked potassium. Why? Because you have more shells, further apart, larger atomic radius. So what's the relationship between calcium and nickel? Ooh, I think they're in the same period, aren't they? Okay, so then what? Oops, don't do that. Same period. There we go. That's what I was trying to do. So what do I do if they're in the same period? Which one is going to be bigger? The idea is calcium is going to be bigger. Why? Because within the same period, you have less protons, therefore less attraction. They're further apart, so you have a larger atomic radius. Okay. So what about gallium and boron? Hey, they're in the same group, aren't they? Looking at that periodic table, so which one's bigger? Gallium is. Why? More shells, the same answer up here. More shells, further apart, larger atomic radius. Oxygen or carbon? They're in the same what? They're in the same period, aren't they? So which is going to be bigger? It's going to be carbon. Why? Less protons, less attraction, further apart, large atomic radius. If you want to, I can put those in the blanks, but it's the same reason over and over and over again. So what's the relationship between chlorine and bromine? They're in the same group again. So which one's bigger? Bromium. Why? More shells, further apart, larger atomic radius. Beryllium or barium, they're in the same group, aren't they? Ruh-roh. Come here. No, sorry. They're in the same group. There we go. And so which one is going to be bigger? Barium. All right, why? More shells, further apart, larger atomic radius. Okay. What about silicon and sulfur? They're in the same period, aren't they? Okay, so now what do I do? Well, which one is it going to be, silicon or sulfur? It's going to be silicon, isn't it? Why? Because it has, you can do it. Oopsies, go away. It has less protons, less attraction, further apart, larger atomic radius. Now, what do I do with iron and gold? Here, let's find iron and gold. Let's look up at the periodic table again. Iron and gold. Let's see here. Iron is right here, and gold is right here. What direction are these? They're this direction. So what's the problem when it goes that direction? I wrote, you can't really tell. All right, you can't really tell, cannot be determined. I said most likely gold, as it has more shells, because iron isn't that far away, or it's not in a vastly different group to make a huge difference. All right, but that's a difficult one. So I'm going to put kind of like in the middle. I don't know. All right, yes, I really do. We can look up those numbers and determine it. But just by looking at trends, you really can't tell. So once again, if the diagonal goes in a negative slope, you really cannot determine it. But if the diagonal is going in the opposite direction, a positive slope, then it's a no-brainer. Okay, it's a win-win situation. Hopefully this is getting a little bit easier for you. Okay. Okay, I'd like you to go to the next page. And this is all about ionic radii. So you have in your homework packet a graphing activity on ionic radii. So what I'd like you to do is go to page, let's see here, 6, 7, and 8, okay? And we're talking about the atomic radii. And what's an atom? It's that charged particle. So if you get out your colored periodic tables, remember we wrote usual charge, so group 1 is usually +1, group 2 is usually +2, noble gases are 0, halogens are -1, oxygen family is -2, nitrogen, phosphorus are -3. So if you find those usual charges, that's what we're talking about. So what happens when sodium becomes sodium plus? What happens when fluorine becomes fluorine -1, okay? So go ahead and I'm going to stop this video. Please go ahead and do that graphing activity now, and then come back to your notes and we'll finish up this section, okay? All right, don't wait to be great. See you next time. Bye-bye.